Okay, welcome back to this second part of the morning. We have another very interesting lecture today. It's a pleasure to have here Catalina Curceanu. Catalina, senior researcher at Laboratory Nazionali Frascati, is well known in this environment because she is the director of this INSPYRE International School, exciting school, I have to say. And among others, other responsibilities, she is responsible of the Siddhartha-2 experiment at the DAFNE collider. And today, indeed, she will talk about the strangeness in the neutron stars investigated at DAFNE collider in Frascati. Please go ahead, Catalina.
Thank you, Pasquale, and thank you for everybody who's connected with us. Good morning to everybody. It's a pleasure to be back with you in this connection. And I greet you from wherever you are connected. So if you have looked or heard the first lecture this morning, you will find mine as being somehow a continuation and a prolongation of that lecture, in the sense that we will also talk about stars, a very peculiar type of stars, namely the neutron stars. And I will tell you and show you how you can also study stars, not only looking in the universe and trying to make measurements on them, but also how you can do experiments in a particle-antiparticle collider, so in an accelerator, to try to get some information which you use afterwards to have an insight in the star physics. So before starting, we know that the universe is filled with stars. This is a kind of a movie starting from the famous Van Gogh painting, which I like very much, which shows some stars. But of course, in the universe are much more than in this painting. Actually, if we look in the night, during the night at the stars on the sky, we see so many of them that it's unbelievable. They are, of course, very, very beautiful, but it's hard to see neutron stars as well, as it's impossible to see isolated black holes. And we will focus in this lecture on the neutron stars. But before doing this, let me tell you that in the universe, there are hundreds of billions of galaxies, and each one of these galaxies contains, in turn, hundreds of billions of stars. So the star, it's, let's say, kind of an atomic element, if you want to say so, of the universe. It's so present in the universe, but there are so many different stars. Some are big, some are little. Some stars like our own, it's a kind of a, medium-sized stars. And the star, we are used to it because right now, I mean, the sky, it's in the sun, it's in the sky, it's shining. And we also know, we learned how is the physics which makes a star shining and keeps it alive. So what's the fire which burns inside the star? Why it is shining? And why a star keeps alive for many, many years? Of course, that the life of a star depends on its mass. Bigger is the star, shorter it's its lifetime. And our sun, now we are in the middle, more or less, of its life. And its life is going to be kind of 10 billion years. Now we are in the middle. And what we know about the stars is that they keep alive as long as there is an equilibrium between two different types of forces or pressures, let's say so. One, it's given by the nuclear physics processes which occur inside the star. And this type of processes are the nuclear fusion, which, if it wouldn't be any other force opposing to it, it would make the star explode like an enormous nuclear bomb. But there is another force which is opposing to the explosion, and this is the gravity. So the gravity force. So as long as these two forces are kind of keeping in equilibrium, the star lives and nothing, let's say, happens. But of course, Now I show you one of these nuclear processes. It's the nuclear fusion, which is proton-proton fusion, as you see there, producing a deuteron, so a heavier hydrogen. Another proton comes, which it's giving rise to a photon. And then if you take two of this nucleus, which are the helium ones, you might form the helium-4. So this is a kind of a prototype. Of course, it's not only this, one can get towards heavier elements, but this is the type of nuclear fusion processes which are occurring inside the stars. And depending on how heavy the star is, well, for heavy stars, like heavier than our sun, these nuclear fusion processes are going on towards heavier and heavier elements, so that in the heart of a star, there are elements which are born, which go from helium, which I showed you before, towards carbon, then towards oxygen, neon, and manganese, silicon, up to iron. Well, up to an iron, we can't forge heavier elements inside the stars. And this, it's because to forge heavier elements like uranium or lead, for example, you need to have energy to make this nucleus collide and fuse to beyond the iron limit. So the heavy elements usually are born during the star explosion, namely during the supernova processes. So when you want to arrive at having burned up all the nuclear processes which can occur inside a star, what happens is that the equilibrium between the two forces, or between the two pressures, to be more precise. I see a question that Fafone said that gravity isn't a force. Actually, we are still using the two languages. In reality, it's true, gravity is not a force. That was the language used by Newton, and somehow we are still using it, even if it's not the exact word. But let's say the two pressures, the nuclear pressure, which is generated by the nuclear fusion, and the gravity pressure, which is generated by the gravity interaction. So when you have arrived to consume all the nuclear fuel, there is one of the two is going to be missing. So the nuclear pressure from inside can't compensate anymore the gravity. And this is the moment in which a star dies. And the death of a star depends very much on which is its mass. So if the star is big, namely 10 or even more, 100,000 times more than our sun, what happens is that it gives rise to a supernova, which is a very, very powerful explosion of the star, when it reaches these final moments in which you can't compensate gravity any longer with nuclear interactions inside the star. And this explosion sends in the universe big part of the matter which has been forged inside the star, but not all of it is spread in the universe. Part of it, namely the core of the star, it's going to collapse under gravity. And the collapse generates function of the residual mass. So if the mass is not very big, it's kind of 10 times the mass of the sun, it gives rise to a neutron star. If the mass is even bigger, what happens is that the gravity, it continues to shrink and the mass, and what it's born, it's a black hole. What we are focusing today on, at least in my lecture, are the neutron stars. And we want to learn what happens, and what you have heard also from Viviana, that what stays, what type of matter it's inside a neutron star, it's basically unknown. So that's more or less what it's assumed to be a supernova explosion. And a big part of the matter including those type of nuclei, which I told you before, the oxygen, the carbon, the nitrogen, the silicon, and well, are spread inside the universe, while much more are formed, like heavy nuclei are formed in collisions occurring exactly in this final explosion of the supernova, which means that, well, what remains can be a neutron star, and I'll talk mostly about this and about experiments we do in the lab, in particular in my group, to learn more about this type of neutron star. This is also kind of a poetical statement, because the elements of life beyond hydrogen, hydrogen is the only element with some component of helium, which are created immediately after the Big Bang, while all other elements, including the elements of life, are born inside the stars by the processes I told you before, namely this nuclear fusion. So this type of processes are very important, and are those who in the end forged our body. And at this point, I want to ask you if there are some questions about this introduction.
No, Catalina, for the moment, we didn't get any questions, so you can continue and stop maybe in a while.
Okay, so then let's go on. So that was a very general introduction of how star, and in particular neutron stars, are born. And it happens that part of these neutron stars have very, very intense magnetic field, billion times more intense, even million of billions, so 10 to 15 times more intense than the magnetic field of the Earth. And this generates radiation, which is specific to type of neutron stars, which are called pulsars. So this type of stars, which are neutron stars with radiation coming from magnetic field, have a very funny story. They have been discovered in '67 by Jocelyn Bell Burnell, and it has been observed like a radio source emitting regular, so this type of radiation, each period with a length of 0.04 seconds, long pulses. And initially, the regularity of these pulses was very weird, because people were not aware. So this type of pulsars were not predicted before their discovery. And this type of signal, I repeat, was a radio source, was so weird that somebody thought that it might be due to some extraterrestrials which are trying to send us some messages and try to communicate with us. Fortunately, soon after, it became clear that these are natural signals which are sent to us not by extraterrestrials, but by this type of stars, so neutron stars which are emitting this radiation. For today, there are many more known, there are many sources of this type known, and they are actually representing an important source of knowledge and of studying these fascinating objects. Good. So neutron stars are very, very peculiar objects, because their mass, it's kind of, well, 1.5, but even 2, I will show you later, times the sun mass. But their radius, it's very small. You see here a picture of a neutron star, a kind of a drawing, imaginary drawing of a neutron star, let's say near the Vancouver. So the radius is kind of 10 kilometers of this neutron star. So it's like if you take two suns, one sun and another sun, and you squeeze them in a radius of 10 kilometers. Of course, that in this condition, the matter density, it's really, really, really extreme. And I'll give you two examples of how extreme this density is. One is taken from Neil deGrasse Tyson, who says that to achieve this density, one needs to have a herd of 50 million elephants into the volume of a thimble. A similar way of saying that is that now, of course, it's not time to do parties, but let's assume that soon after coronavirus it's ended, we will do a party. And let's assume that I want to do a party and I want to invite people at my house. And how many people can I invite in my house? Well, let's say maybe 20 and we are comfortable. But if we would be matter from a neutron star, I could invite not only all my city, which is Frascati, not even all Rome, which is the biggest city nearby, but I could invite all Italy, even more. I could invite all the people in the world, 7 billion people in the world, and I would give the party in a thimble. So that's how dense it's a neutron star. Extremely, extremely dense matter. And by this point of view, a neutron star has a density which is not so different from the density of a black hole. You see here an example of a neutron star and a black hole, both of them having the mass 1.5 times the mass of the sun, and you see that the radius of a neutron star, it's only twice the one of a black hole. So studying the neutron star, somehow you're also approaching the density conditions which are inside a black hole, somehow being able to have a kind of a physics study in more controlled and not necessarily easy, but somehow possible condition to understand something and to access in the future also the black hole. So now what's the problem with the neutron star? The problem is that in spite of the fact that they are called neutron star, which might make you believe that neutron star are well known and they are made out of neutrons, they look somehow like a huge nucleus which are inside the atoms, but nucleus made entirely of neutrons containing something like 10 to 55. I repeat, 10 to power 55 neutrons, one might believe that its neutron star is like that. But actually, and in the last couple of years, the discussion became extremely hot in the community of astrophysicists, especially the nuclear physicists who are studying astrophysics. And the discussion became very hot because it's not very clear. It's not clear of at all what stays and what type of matter is inside the core, the heart of a neutron star. And I'll show you now what could be an alternative to the neutron star matter, and I anticipate it's strange matter, namely matter containing the strange quark. Not that this is yet established, but it's an hypothesis which is worth considering. And this discussion has been going on for quite a while. What is contained in the neutron star, but right now we are approaching, by experiments done in the lab, a kind of a period or an era where you can also have some information from experiment which helps you to understand the matter in extreme conditions. And this is what it's called the equation of state of a neutron star, which means that what you see actually in this graph is the following thing. So on the y-axis, we have the mass of the neutron stars. While on the x-axis, we have the radius of the neutron star. Now I have to tell you that the radius of a neutron star, it's unknown. We know that it's around or about 10 kilometers, but there is no precise measurement of a radius. It could be 7 kilometers, or it could be very well 15 kilometers. There are telescopes and measurements which are undergoing now, which hopefully will succeed to pin down better this radius. But for the moment, what we know with high precision, it's actually the mass of the neutron star. And Actually, it's very interesting because it has been discovered that there are kind of two families of neutron stars. One with mass around 1.4, more or less, 1.5, the big majority of the sun mass. While very recently, some two solar masses neutron stars have been discovered. So these are the masses and the physical objects which have been discovered. While these curves you see here are the equation of state prepared by theoreticians who have kind of made a recipe of what you'd expect between the connection between the mass and radius on what we know from the nuclear physics. So this equation tell you what would be the evolution of a neutron star, but the ingredients you see are very different. So there are the green curves, which are taking a kind of equation based on some assumption. Why there are blue curves or even red, some of the red are excluded because you see they are unable to predict even the lowest mass neutron stars. So theoretical predictions are the curves you see here. And they are still open. Many of them are still open in the sense that some of them are including strange matter, so strangeness, as I will tell you in a short inside. Some of them are saying strange matter, it's not necessary. Why there are so many curves? Part of them, it's not only because the radius information is missing, but also because information from nuclear physics is missing. And I'll show you how we provide part of this information. Now I give you some time. If you have some questions, we may discuss.
Yes, Catalina, we got a lot of questions. So first of all, a neutron star is made of neutrons that are neutral. So in which way they can generate a magnetic field?
Yes, so the magnetic field of the star is generated by, so this type of neutrons have, the neutron has a magnetic moment. Well, there are circulating particles. It's not only neutron, there is still some electrons and protons residuals in a neutron stars, and it's spinning very, 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 very fast. And this spinning of a neutron star, we know that a rotating current or rotating charge is producing a magnetic field. And since this is the kind of a very, very fast rotation, the magnetic field can be also very, very intense. This type of stars are called magnetars. So the stars which are having a very intense magnetic field. So what stays inside the neutron stars, as I'm telling you now, is not completely known. So the assumption of being made only of neutrons, it's a very simplified assumption. Actually, there are some residuals of electrons and of protons, and maybe even more, as I will show you in a while. And electric charge in rotation is producing magnetic fields.
And I guess connected to this, the question is, we know normal stars, how they can bright by the fusion mechanism, but how a neutron star can be seen? So how can be bright?
So the neutron stars usually are seen like pulsars. So what I told you is that kind of emission of radiation when you have this very, very intense magnetic field, which is producing this radiation. Of course, you have to be very lucky because you have to be, so this radiation is produced in very sharp direction. So Earth should be in the direction of this field, of this electromagnetic field, in order to be able to see it. That's one way. The other way, which has been discussed also by Viviana, which has been set up rather recently, is this, waves, the gravitational waves produced by the neutron stars. And in this case, again, very, very few events have been seen up to now, but we hope that in the future, more and more events of these types will be seen.
So last, before continuing, can a neutron star eventually become a black hole?
By itself, it can't. So a neutron star, once it's formed from the collapse of the star which produces it, remains like that. So it can't spontaneously produce a black hole. It still can produce a black hole when it finds itself in a binary system, either with another star, so a normal star of a certain mass, or with another neutron star. So in the end, a binary system in which one of the component, it's a neutron star, can, as a result of the collapse of the binary system, result in a black hole.
Okay, Catalina, yes, we can continue with the lecture.
Okay, thank you very much. So let's go on. That was a very brief introduction to the genesis and to a kind of a, well, not necessarily structure, but unknown structure of a neutron star, and the reasons for which we don't know this structure, which are coming from one side, the fact that we don't know its size. On the other side, it comes from the fact that we don't know the nuclear physics processes well enough to put them inside our equations and have a theoretical insight which can predict precisely what happens inside a neutron star. Now let's see how we can do this inside our lab. So how can we connect the neutron stars with the particle physics, in particular with the nuclear physics processes, and in specific with the physics experiments, what we do inside our lab on our accelerator, which is called DAFNE. Before doing this, let me briefly remind you that the normal matter, the stable matter we are aware of, it's formed from atoms. So the atoms which have been discussed previously have a structure which is composed, which is seen inside a small nucleus. Here we have the helium atom, which contains 2 protons and 2 neutrons inside their nucleus, surrounded in orbit by 2 electrons. And when we go to a smaller structure, so towards elementary particles, we know that this atom is formed from quarks. Actually, each neutron and proton, it's formed from the 3 quarks. And in the proton, we see that there are 2 up quarks and 1 down, while in the neutron, 2 down quarks and 1 up. And also, I mentioned to you that in the particle accelerators, much more than these particles I mentioned here, so 2 up quarks and the electron and down quarks have been discovered. Actually, there is an all particle zoo, which will be discussed even more tomorrow in the lecture on the LHC related physics. So I'm not going to insist on this. But for what it is important today is that beyond the up and down quark, which are forming the stable matter, so all the matter which is stable, I repeat, it's formed from only these 2 types of quarks, up and down. But in particle accelerator experiments have been discovered more quarks, like Strange, which is the smaller mass among the 4 remaining ones, Charm, top and bottom. These quarks are belonging to particles which are born inside accelerators, but they live very little, so they decay towards more and more stable particles, leaving no trace from their existence in very, very short time after they are born. So their lifetime span between something like 10 to minus 11, let's say 10 to minus 8 seconds up to 10 to minus 21 seconds. So they live very short. And up to now, from what we know, none of this quark is found in stable matter. But this is going to be questioned exactly now in the conjecture that the neutron stars might contain the strange quark inside as a form of stable matter. So that's kind of what I told you before. It's a kind of a summary. So the matter, the stable matter built up of atoms, it's containing quarks and electrons, but for what we know in the stable matter, only these up and down quarks belonging to the so-called first families, so the standard model of elementary particles and interactions. Actually, it's containing all these particles that I show you here, and only the first family, which contains up, down, electron, and the neutrino corresponding to the electrons, are forming stable type of matter. The other ones, the second, the third families, are not belonging to any sort of known stable form of matter, but they are formed either at the particle accelerators or in interactions of particles coming from the universe, so-called cosmic radiation in the Earth atmosphere, so they can be also studied like this. And what I'm going to conjecture and tell you about in this lecture, in the remaining part of the lecture, is how could it be that in the neutron stars, for the first time in what we know and in the universe, a third type of quark, namely the strange quark, can have a different role and can become a component in a form of a stable matter, namely the neutron star, which at this point the name neutron star might not be even right if this is true. So you might see here that why we take the strange quark in account and not the others, just to anticipate to you something what I'm going to tell more in detail after, it's because among the remaining quarks, the strange one is the one which has the smallest mass. So the mass in particle physics is measured in electron volt, which is an energy unit. Energy is equivalent to its mass, which energy belongs to what is the kinetic energy of an electron accelerated in a potential difference of 1 volt. And by this point of view, we see that the strange quark has a mass kind of some 10 times bigger than the up and down, while the other ones are much heavier. And well, the standard model is the answer to the normal matter, but only to the first family. I repeat myself, so only first family belongs to the stable form of matter. But so what we want to, why we consider the fact that the strange matter and the strange quark interaction might play a role in the neutron stars. So one of the things which are lacking those theoreticians, namely nuclear physicists, who are working with this equation I showed you before and which are spanning very different portions of the radius against mass fraction of the neutron stars, are lacking the strength. So what they are missing is how strong it's the interaction of particles having strangeness with normal type of matter. So the possibility to find strange matter, namely strange quark, inside a neutron star depends on how strongly this strange matter, strange particles, which I'm going to show you in a minute what they are, so how strongly they are interacting with the other type of matter. According to the strength of this interaction, there is more or less likely to find the strange matter inside of a neutron star. And this is exactly what we are measuring in our experiment. We are quantifying and measuring how strong is the strong interaction between a strange particle, I'm going to show you in a minute what strange particle, and prototypes of normal nuclear matter. So we measure the strength of this interaction, and if the strength is very high, it means that you might form, so nuclear interactions might start may start in the neutron star, give birth to strange particles which bind themselves with a very strong glue. If this is the case, and that's what we don't know, they might form strong binding and very strong glue with the other matter and remain there because energetically it's more, it's easier, so it's favorable. It's all a matter of energy. So nature, by this point of view, it's rather lazy. It does things which are easy, which are the most convenient things. This is the principle of minimum action, for example. So if energetically it's easier to form and glue strange matter, this is what will happen in a neutron star. Now let me tell you, before telling you what our experiment is doing, let me go a step backward and tell you why we are able to do this type of experiments here in Frascati. And this dates back, you see, more than 50 years ago with this beautiful accelerator technology, which allows to me and to my group to do experiments today on studying neutron stars in the lab. But everything dates back early 60s, when for the first time in the world, for the first time ever, the collisions of particles and antiparticles, matter, antimatter, has been experienced to form new particles and study interaction in the universe. So I'm going to tell you how colliders have been born in Frascati, and I show you here, I'll show you again in a while, this accelerator, which is called ADA, Anello di Accumulazione, which presently it's in our open air museum, and I hope you will come sometime and see it and with your eyes, and which now became a historical site of the European Physical Society. So before we have set up this interesting collider in Frascati, accelerator existed even before, since the 40s of last century, but they were kind of simple accelerators in the sense that a beam of particles, electrons or protons, were always colliding on a fixed target. So fixed target like a piece of metal or a gas or a liquid. And this was a very nice technique, but had some drawbacks, some limitations. Well, the limitations are quoted here, and part of them are obvious, like, for example, target, it's complex. So if I want to study interactions between proton and proton, well, I can't do only that because the target is composed of atoms, which also contain neutrons and electrons. Matter, it's mainly empty in the sense that atoms are, well, you know, the relative dimensions between electrons and the nucleus, it's kind of 100,000 times smaller. So basically matter, it's empty. So it's difficult to collide particles you want and how much you want. Moreover, you are limited with the energy, and this is the statement, energy lost by moving the center of mass. So the energy is brought into the game only by the beam of the particles. The target particles are stopped, so they are not moving. So, which means that the first Frascati idea, which came in the group of guys, they were all very young, led by Bruno Tuschek in early 60s, seems to be a very useful but trivial idea. Okay, if you have all this limitation, why not then, instead of having only one beam colliding with a fixed target, why not colliding a beam of particles with a beam of other particles, for example, antiparticles? Now, this, I tell you, of course, you have a lot of advantages in this case. You can, if it's circular, you can reduce the beam because you recirculate it. You bring more energy because you have energy in both beam. You can annihilate. You can do whatever you want in a much more flexible way. But in spite of the fact that this idea looks very simple, its realization, it's complicated, because this means, first of all, you need to, in order to collide them, of course, you need to bring them together. But bringing them together, it's not easy, because in order to have some success to collide them, head-on collision, of course you want to have many all together. So you want to have billions against billions. Then it's kind of more likely to have head-on collisions. But this puts you a problem, because to keep billion of particles inside the beam, remember, we can only accelerate charged particles. So it means that, for example, I need to put billions of electrons together, but electrons are alike charged. And it means that they don't want to stay together because there is repulsion. So they kind of hit each other, kick each other, and if we don't oblige them to stay together, they won't. Which means that we need to invent skillful technologies to keep them together. And this is not easy. So the realization of this idea, it's complicated. Then the second idea was, let's do, as I told you before, not particle collision of whatever type of particle, but at least in Frascati case, differently is the case of Large Hadron Collider, we make annihilation of particles and antiparticles, which means that all the energy you put in, including the masses of the electron and positron, plus their kinetic energy, what happens is that this can be transformed out of the energy conservation in mass of the particles in the final state. So we make full use of the Einstein formula, which means that the energy of the particles, electrons and positrons in our case, materializes in mass of the final particles. And I'll show you what exactly we do. So what is the process we use in our strange particles experiment? So this was an introduction to Frascati and what was the role of Frascati starting by early 60s in producing this type of technology and this type of accelerators. And what you see here again, ADA, it's not actually an accelerator which has been used for physics, because when physicists by that time went to the ministry and asked for money to build this type of interaction, or this type of accelerator, the government, Italian government of that time asked them, but who else in the world built this? And they said, nobody, we are the first. So they said, oh, then you don't know if it works. So we give you money not to build accelerator, but to build a prototype. And that's what has been done, a prototype very successfully showing that electrons and positrons can be collided, in this case producing only photons, so the annihilation produced photons could be built. And then money were given. A first accelerator called DAFNE was built and very successfully used to investigate the, by that time, fashionable standard model, which was not yet very well known. And presently we have the same, but with 1,000 times more particles produced per second. That's the reason for which you see the very complicated structure of DAFNE collider. DAFNE comes from a double annular 5 factory for nice experiments. Okay, so this is the accelerator seen from outside. This is a picture, an overall picture from inside. And as I told you, it's a rather complicated machine. You might see here a picture from above, which contains a lot of elements. You might see these white cylinders, which are vacuum pumps. And these vacuum pumps are necessary because the particles are circulating into beam pipes where the vacuum needs to be realized. Otherwise, they would not circulate, but they would be stopped and interact with the residual gas. There are all sorts of magnets, and that's how it works. So, moreover, these techniques, it's realized not only in Frascati, but it's being used presently also in other accelerators, like the one in Geneva, the Large Hadron Collider, where at much, much higher energies, proton against protons are collided. And here the fact that they don't use antiparticles, but they use in both beam protons, it's not relevant. I mean, it's relevant in the sense that it makes life easier, but the energy in this case is not relying on the mass of the particles, but it mostly relies on the fact that these protons have very, very high kinetic energy. That's normally how an accelerator works. So there are electric and magnetic fields. Electric fields usually are used to accelerate. Magnetic fields are used to bend and to squeeze the beams. And it's a complicated technology which is even today being developed. And it's used to create, accelerators are used to create and to study new types of particles, or to create and study, if they are not new, particles which are known but are unstable, like the particles I'm going to show you, namely the strange type of particles. And questions?
Yes, Catalina, we got several questions. First of all, what makes us thinking that the neutron stars have an inner structure? Is just by theory, or we have some experimental evidence?
What makes us thinking that there is strange matter?
Well, strange matter and inner structure is not just a bulk of neutrons altogether.
Well, that's coming today mostly from theoretical developments. So we don't have experimental information on neutron star itself, at least because experiments, measurements, even of the gravitational waves, are not precise enough. So it's based completely on nuclear physics, which proves that between nuclear physics and astrophysics, there is a very intensive connection, a bridge which brings you both ways. And so it's theoretical development, which makes us believe that strange matter could be inside a neutron star.
Good. How do we measure the masses of neutron stars?
So how do we measure the mass of a new? I'm not an expert on this type of measurements, but at least for the last two types of measurements has been used the general relativity. So general relativity effects, which we know general relativity makes that the bending of the geometry depends on the mass of the objects. And the last measurements, especially those which gives the neutron star masses, has been done by using general relativity to measure the neutron stars. General relativity has been also used in the past actually to measure the mass of the neutron stars, and it has been awarded Nobel Prize for this. So it's an interconnection between general relativity and astrophysics, and very precise measurement of different kinds in astrophysics using, for the moment, telescopes. And we hope in the future that more information will also come from gravitational waves, from precision measurements like Viviana has shown before, in the next 10 years or so, from a different type of gravitational antenna, which would come together and give us more information independently of what telescopes could measure.
You said that the neutron stars are a connection between relativity and astrophysics. But Andrea asked, is it possible to think that the neutron stars are the natural unification between general relativity and quantum physics? So it's not an easy question. Huh?
It's not an easy, it's actually a very, very beautiful question, because it's a beautiful question in many ways, because neutron stars, why a neutron star does not become a black hole? Actually, for quantum physics, there is the Pauli blocking, which is the Pauli exclusion principle, which acts on the neutrons, which are fermions, which are not collapsing anymore because of the degeneracy pressure induced by quantum physics. So by this point of view, I mentioned this because I have an experiment, I'm not going to show it today, in Gran Sasso Lab, which we are trying to check whether Pauli exclusion principle might be violated. So by this point of view, in my opinion, the neutron stars are one of the most beautiful objects in the universe, because they are there, like with quantum physics, with general relativity. You can measure them differently from black holes. You can measure them with all sort of physics, with all sort of interaction, because you can measure the electromagnetic radiation, you can measure gravitational waves, and you can measure nuclear physics. So you have access from all sort of information differently from any other objects, let's say, any other so extreme objects. So yes, there is everything there, and it's really beautiful objects where quantum meets general relativity.
So last, before continuing, you said that the strange particles are unstable. How can be that they are stable into a neutron star?
Yeah, so yes, in our normal density conditions, strange particles are completely unstable. You can stabilize them if, for example, let's assume that let's assume now, sorry, I'm trying to give a very crazy, let's assume this is a strange particle. A strange particle has its own mass, and if I create it with the accelerator, it immediately decays, dies out, and I don't have it anymore. If I have a strange particle, actually more than one, let's assume I have 3 strange particles. Let's assume this color is strange particle. And if the interaction, and let's assume these are normal neutrons or normal particles, if the interaction, so if I have many, like in a heart of a neutron star, and if the interaction, if the binding energy, so if this strange particle is bind inside the core of the neutron star with a very, very big binding energy, its effective mass, so what looks like its effective mass, which is not the same as the free mass, its effective mass goes beyond the threshold of decay. So it cannot decay anymore because it has nothing to decay in. Its mass, effective mass, due to the binding energy in extreme conditions, namely with so many particles inside the heart of a neutron star, which we can't create in the lab, would make so that its effective mass, sorry, I lost a neutron, its effective mass, it's beyond its mass which can be decayed. But this, of course, it depends on how strong its binding energy. And this is exactly what we want to measure, because if the binding energy is not strong enough, it will still decay and it will never be there as a stable form of matter. If binding energy is very strong, it will give to the strange particle an effective mass, which would put it below the threshold of any decay, setting it as a stable particle, stable bound particle.
Okay, thank you, Catalina. We can now proceed for the last part of your talk.
Thank you very much. Okay, so this kind of makes my life easier from now on. How we do, what type of interaction, what interaction we study. So what we are doing in our experiment, it's what it's called kaonic atom spectroscopy. So we form and study exotic form, which means atoms which do not exist in reality, in nature, but they are exotic in the sense that we replace, in our case, the electrons with a different type of particles, which has, again, a negative charge. Otherwise, it wouldn't be able to form an atom. It's bound by the nucleus with the electromagnetic interaction, which defines the fact that it is an atom. But as I said, it's not an electron. In our case, the particle which it's bound in the atom, it's a particle which is a strange particle, so it has the strange quark in it. And what is the particle we use? It's the negatively charged kaon. So in the DAFNE machine we have in Frascati, the collisions between the electrons and the positrons, it's tuned, so which means that the energy of the beams is calibrated such as to produce a particle which is called a phi particle, which we don't study. So what we use it for, it's as a kind of an intermediate between the interaction between electrons and positrons, and the final states kaons, which is a particle which has the strange quark inside. What we use is the negatively charged kaon, and now let me show you. So the kaon, it's a particle which contains the strange quark. So it's a quark, strange quark, which is bound with an anti-U quark. It's a quark and an anti-quark. For whomever has ever heard this word before, it's a meson, so it's meson family. While the proton and neutron are quoted here. One is two quarks up and one down. The other one, I repeat, two down and one up. So we use the kaon, negatively charged kaon, because it contains the strange quark. So this helps me to measure somehow the interaction between a particle containing strange quark and the normal type of matter. And what we are actually doing, you know, this is a normal atom, but we don't use electrons. We replace the electron with these negatively charged kaons produced inside the collider. And what we are actually studying is the electromagnetic radiation, which is produced by the decay. So this is the excitation of a normal atom, but the same is happening also with an excited exotic atom. So now let me tell you more about how this is going. Actually, let me go to this. So we have a beam of kaons, and the beam of kaons, which is produced by the accelerator, we shoot it inside target. In our target, we have, well, in our case, we have either hydrogen or deuterium, because the first thing we want to measure is the interaction between the kaon and the proton, and the kaon and the neutron, which is contained inside the deuteron, which is a heavy hydrogen containing a proton and the neutron. So the kaon enters inside the target, it meets an atom, and when it meets an atom, actually it sees the electron in the last orbit, and since the mass of the kaon is 1,000, I repeat, 1,000 times bigger than the mass of the electron, it kicks the electron and replaces it inside the atom, forming a kaonic atom. So it kicks the electron goes away, and the kaon gets trapped inside the atom, forming an exotic atom. Now, one might be worried that I told you that the kaons live a kind of 10 to minus 8 seconds, but all this process, which I'm telling you, the use of the beam, the formation of the atoms, and the decay of the atoms, it's lasting much shorter. So for our purpose, the decay of the kaon do not play a role, because we use to form these atoms and study them in time period which is much shorter than the lifetime of the kaon. Once the kaon is trapped inside the orbit, it forms, exactly due to the fact that its mass is much higher than the one of the electron, the formation results in a highly excited kaonic atom. As a highly excited atom, it doesn't want to stay in that state of energy, but it decays. So it de-excites, going to the fundamental orbit, namely the one closest to the nucleus, by emitting radiation. In this case, the radiation in its X-ray domain, so not visible like the normal atoms, but X-rays, much higher energy. Now, the interesting thing comes now, that when the kaon goes towards the lowest orbit, so the one which is closest to the nucleus, it feels not only the electromagnetic interaction, because it is charged, so there is electromagnetic force between the kaon and the nucleus, but the quarks inside the kaon are feeling the strong interaction with the quarks inside the nucleus. And basically, what drives the interaction is the strange quark. So this strong interaction overlays on the energy, and it's shifting it. So it has an effect. If it would be only electromagnetic, it would have a value. But the strong interaction, it's shifting this value. And it also produces, but that's, I'm not going to insist on this, it's also in the end killing the kaon, because the kaon, it's eaten up, it's absorbed by the nucleus. But let's forget about this for the moment. So the orbit, it's shifted, which means that if you measure the energy of this radiation, and if you know the electromagnetic value, the difference between what you measure and what you calculate, taking into account only the electromagnetic value, it's to be ascribed entirely to the nuclear interaction corresponding to the quarks between the kaon and the nucleus. So this is an indirect way, actually the only way, where you can measure the strong interaction between the quarks, including the strange quark. And this is another way to say the same thing I showed you before, but I will leave you this in the slides. I'm not going to comment it right now. What I'm going to show you is how in practice you do this. So we have electrons, positrons colliding. Negatively charged kaons are delivered. They form kaonic atoms inside the target. They emit X-rays, which should be measured by X-ray detectors. Then if you do a nice measurement, you can compare the measurement with purely electromagnetic calculated value, and the difference between what you measure and what you calculate electromagnetically, it's the corresponding nuclear interaction component, which tells you in the end, should tell you in the end, if what I showed you before, is this interaction strong enough to produce or not a strangeness in the heart of a neutron star. And here it's comes some technical details. So up to now we measured hydrogen. We are now measuring deuterium. And we keep the hydrogen, of course, inside the target. We keep it in conditions of high density to form more atoms, which is realized by having a very cold target, 20 Kelvin, and overpressured. We measure the radiation with silicon drift detectors, which are very nice silicon detectors, which we use to measure X-rays, do spectroscopy of X-rays. So we have everything inside a so-called vacuum chamber, because in order to have nice spectroscopic measurement, we have to cool the detector down to -100 Kelvin, to -100 centigrades. So we need to put inside vacuum, otherwise water vapors would crack, forming ice. And that's the real object with the real detectors, and that's my group inside the DAFNE, where we have installed, and we were just now in the phase of measurement when this problem of COVID happened. So we are right now, in the past, actually that's a very broadly international collaboration containing people coming from practically all over the world: Italy, Austria, Romania, Germany, Japan, Croatia, Poland, and it's a very, very nice environment. We have measured in the past the hydrogen, which means that we have, this is the spectrum which we have measured, while the lines you see here are the electromagnetic value. You see that the peak, it's not on the electromagnetic value, but it is shifted, and the shift corresponds to the strong interaction between the strange particle, which is kaon, and the proton in this case. What we want right now is to measure the deuterium, to have also a handle on the interaction with the neutron. This is not the real measurement, but it's a Monte Carlo simulation. So this is what we expect to have. We were hoping to have it this year, but now we are stopped. We hope to be able to start again within summer or as late as in autumn. and hopefully to get a measurement with this precision. Now, this comes back to the neutron star, because look what's the situation. So I show you now, this is the shift, what we expect to measure, and also the lifetime of the state, what we expect to measure. And the points here are theoretical prediction. So theoreticians are absolutely not in agreement. So each one takes different type of assumptions, and they have extremely different predictions. What's true, this or this? While our measurement should have this precision, what you see here, but we don't know, of course, where it will stay. Might stay here, might stay here, here, or might even stay here, where is no theoretical prediction. So everybody is awaiting our measurement, because this sets the basis of the theory with strangeness, and then that theory with strangeness later on reflects into the theory of a neutron star. Theory which is very exciting, because it goes beyond the neutron star with strangeness. There is some discussion undergoing now, and even some quarrel about the possibility to have not so-called neutron stars, but the so-called strange quark stars, which means stars where quarks are not anymore bound into structures, but they are melted. They are free quarks. Density is so high that the quarks become free, and they're up, down, and strange quarks, forming these very weird objects, which are called strange quark stars. And our measurement, so it's interesting by itself, because it tells you something about nuclear interactions of the second family with the first family, but also tells you something about the stars. And by this point of view, I come back to the question which has been already asked. We might also learn something about general relativity and beyond in these extreme conditions, because the neutron stars are the intermediate step just before the black hole gets formed. So we are on the threshold of a black hole, but in much more, let's say, controlled and kind of easy to study conditions, including those which are seeing the formation of black holes coming from melting of a neutron stars. So you see, the physics, actually it's unified. You get the same thing, the same physics, actually, going from particle, nuclear, astrophysics, general relativity. And why not? In this way, we may have some information about the theory beyond the standard model, which might be or might not be the quantum gravity and or something else. So I end up my talk with this very nice part of a poetry of Nikita Gill, who says, "We have calcium in our bones, iron in our veins, carbon in our souls, and nitrogen in our brains. 93% stardust with souls made of flames. We are all just stars that have people names." Thank you very much. These are my finding agencies bodies. So thank you very much, guys.
Thank you, Catalina, for this very interesting talk and this peculiar argument. So we have minutes for some questions. So one question is that really, can we put any kind of particles in the atom, not only a kaon? And what does it mean to if we are able to do this? Can we probe other atomic levels or what?
Super question. Actually, the field of exotic atom, it's a much more extended field than the kaonic atoms. We have put inside an atom antiprotons, and we want to study how antimatter interacts with matter. We have put muons, so heavier electrons, and we have checked some fundamental interactions. We have put inside the exotic atoms some sigma particles, so again, some strange particles. So yes, there are other possibilities, not infinitely many, but there are other possibilities, and they are studying different aspects of fundamental physics, going from matter, antimatter, and asymmetry or possible asymmetry to neutron stars.
Good. So the question is that, but why we concentrate on the strange quarks? Can be that there are also other kind of quarks into neutron star, made of, I don't know, top or bottom quarks.
For the moment, this discussion, they are excluded from discussion. First of all, because they are much, much heavier. So in order to form them, we would need to have very, very exotic physics. So if we don't have strange quarks, it's impossible or nearly impossible to imagine to have charm bottom or top quarks. So let's take it one step at a time. Never say never, but let's now what we do, focus on the strange quark. And if we will arrive to convince ourselves that strangeness might play a role either in a neutron star or in strange stars, like I showed you before, then we might make a step forward and investigate other type of exotic physics, which right now is not favored. But as I said, never say never.
So about your experiment, you didn't start the experiment yet. Have you ever measured something before, and when you think you have new results with the new experiment?
We have measured, so we have performed, this is not the first experiment measuring exotic atoms. We have done experiments 10 years ago and some years ago in Japan, because we are also in an experiment over there. And so we have measured the hydrogen, helium, nitrogen. We plan to measure lead for different reasons. And we hope to have results by next year. So even if we do a measurement this year until we analyze the data, so we hope to have by 2021 the first results, including deuterium.
Okay, guys, I remember you that Catalina will answer to all your questions offline. And this point, I guess we can, I don't know, Catalina, if you want to add something, but we can close here this interesting lecture. And on behalf of everybody, I really want to thank you, Catalina. And I give you the appointment to tomorrow morning for the last day of INSPYRE. So thank you to everybody. Yeah?
Yes, I want in my turn to thank you very much for you having taken some time. And since I want you tomorrow, I want to thank to all of you having joined INSPYRE 2020 and allowing us and also to you to make it a successful edition, not as we planned originally, but anyway, hopefully we reach more people than originally planned, which let's say it's a good part in all what happened. And we wish you to come to Frascati, and if you will come, I hope that you will be able to see also our experiments and infrastructure, including the experiment I was telling you about today. Goodbye.
Okay, thank you very much, everybody. Ciao.
Ciao.